So we're just going to jump ahead to section 7 for a little bit here. This is called the reliability of a measurement. So scientists report measurements very carefully. We do that so that we report all the digits that we're certain of and one estimated digit. So that's called the uncertain digit. So here are two tables showing levels of carbon dioxide in Los Angeles County over the course of different years. This one is showing 9.9, and this one is showing 10. These are in parts per million. So here, 9.9 tells me that the uncertainty is in the tenths of a parts per million. So we could say, well, what the scientist is really telling me there is that is, oops, that's way too fat. Oh, that's the wrong thing, that's why, okay. The scientist means it's between 9.8 and 10.0. So adding plus one in that last digit or minus 1 in the last digit. So they're saying, I know that within this range, very, closely. If we say 10, well, let's look at 9. Oh, no, we'll look at 10. So the last digit here is in the ones place. That would be where the uncertainty is. So then this is saying, well, this is between 9 and 11. That's a much bigger range, right? This is more of a guess than this one is. And so in science, we try to be very consistent in how we report measurements so that somebody reading the measurement understands how closely or carefully that measurement was made. And this is all getting to significant figures. So how many digits do you record? Well, it depends on your measuring device. Okay? And this is something that students tend to find very confusing, but once you see it, it's very simple. So I encourage you to keep asking me questions until it clicks for you. So in science, we say we read between the lines, right? So here we're looking at an analog device as opposed to a digital device. So here we have a pistachio on this little kitchen scale. We're not going to look at the ounces side because we don't do ounces in science. We're going to look at the grams. So we're going to read between the lines. So we're first going to identify, well, what are those smallest lines? What do they represent? Well, down here, this says 10. So that's 10 grams, and this is halfway, so that must be 5. Each of those little lines represents 1 gram, right? And so we're going to look at where the red indicator is. It's between the first line, the 1 gram, and the second gram, right? So that means the mass of this is between 1 and 2 grams. It's 1 point something. So there's no uncertainty in the 1. It is definitely 1 gram. It's between the lines, right? And then reading between the lines, we're going to estimate how far it is between the lines. And this is where different people could come up with slightly different measurements. And it's okay. Because we look at that and we can't tell exactly how far it is. It appears to be less than halfway to me, right? You're just kind of eyeballing it. So it's less than halfway. And so someone might estimate that as 1.2 grams. I think it's like 2/10 of the way from the 1 to the 2. Somebody else might say, well, I think it's 1.3 grams. You're both right. The last digit is uncertain. But why do we even write it down at all? Because there's still information there, right? We may not know exactly what it is, but I know it's definitely more like 0.2 than 0.8, right? So there's information there. We want to keep all the information we can, but we don't want to mislead people that we knew it was exactly 1.2. As it turns out, you can't measure anything exactly. It's a bummer. It'd be nice. So what we're going to do is we are going to estimate 1 decimal place past the smallest division. So here on this little scale, every division was 1 gram. The lines represented 1 gram. So the next decimal place is tenths. If we're looking at a ruler that has 0.1 centimeter lines, what's the next decimal place? It's 0.01, the hundredths, right? A thermometer with 1 degree lines. The next decimal place is 0.1. That's where the estimation is. There's no uncertainty to the nearest degree because it's on this line or it's between these 2 lines. There's no uncertainty about that. Nobody's going to argue about it. Does that make sense? So let's look at these. So this is a thermometer, zoomed in. I'm going to tell you it's degrees Celsius. And so what we want to do is first identify, well, here are the smallest lines. What does each line represent? 1 degree. So we've got the line. Each line is 1 degree Celsius. So that's in the ones place. What's the next decimal place? 0.1, right? So we're going to estimate 0.1, the next decimal place. So here, it's kind of unfortunate because the number's in the way here, but this is 100, and 101, 102, 103, right? So it looks like it's really close to 103, maybe a little bit past, right? So 103 and a little more. There's no uncertainty about the 103. We're all going to agree about that. It's right at that line. There's a line that tells us, right? So we can say, well, this is 103, and then we're going to estimate how far. So Remington says 0.2. You might say, well, I think it looks like it's right on the line. Well, then what do I do? Then I'm going to say 0.0. Because if I just said 103, that's suggesting that I didn't have any of these lines, and I was estimating between 100 and 110, right? Which is very different than the situation we have here. Somebody else might say 103.1. Cool. It's all good. Any questions about that? This is going to come up in lab. So here we have a graduated cylinder with some water in it. And this funny looking thing here is called the meniscus. It almost looks like there's a bowl or a contact lens or something sitting on top of the water. And we'll learn in a later chapter why water does that. But measuring devices like graduated cylinders are designed and calibrated to measure to the bottom of the meniscus. So that's the bottom of this shadow here. So again, looking at this, these are milliliters. So this is 4, and that's 5. So what does each line represent? 0.1, right? So the line is 0.1 milliliter. So what am I going to estimate to? 0.01. So here's 4, and there's 5, right? So this is 4.5. It's more than 4.5. It's less than 4.6. So it's 4.5, and then we have to guess. What do you think? Pardon me?
4.59.
That's a good guess, 4.59. Anybody else want to make a different guess? 8? 4.58. There is no, oops. There's no wrong answer. Everything disappeared. Oh well, it's gone. I don't know what I did. So that's how we record measurements. we need the concept of significant figures so that when we take those measurements and we do calculations on them, we can preserve the concept of how precise they are. So if we took a piece of wood that was 10 feet long, and maybe you measured it with your feet, right? Like, well, is that super precise? No. Maybe it's within a foot, right? Maybe it's between 9 and 11 feet, you're calling it 10 feet. If I divide that in 3 pieces, can I say that each piece is 3.333333333 feet long? No, because I didn't know exactly how long the first piece was. But if you do that on your calculator, that's what your calculator will do. We can't increase or decrease precision just by doing mathematical operations. And so significant figures are the most straightforward way that we can deal with those. The alternative is differential calculus, which I think most of you would like to not do. And I don't want to do it because I did it when I was in college and then I forgot how to do it. So I don't even do that anymore. So when we're talking about significant figures or significant digits, these are the non-place holding digits in the recorded measurement. So they're all the certain digits that we wrote down and the one estimated digit. Those are called the significant figures. And the more significant figures you have, the greater the certainty of the measurement. It's the train. So the first thing we have to do is learn how to count significant figures. So there will be significant figure questions on the first exam, and there will be significant figure questions on the final exam. But I'm not going to beat you over the head with these all semester, okay? But give it a try here. Because again, like with the reading the thermometer, once you see the reasoning behind it, it's easy to remember. We just have to get to that point where we understand why the rule is, and then it's easy. So these are the rules for counting. Yes?
Do you remind me, so I've heard this concept before, and every time what I always get wrong is when it gives you two values with different significant figures. It'll be like 1.05 and 1.5. Which one do you base it off of when you're making the final calculation?
So that would depend on where those numbers came from. If they are the result of a calculation, we have rules for picking which one to use.
Okay.
Yeah. So hopefully we'll clear up that for you.
Okay.
So before we can do the calculations and look at those rules, we have to learn how to count the significant figures. So all non-zero digits are significant. So you look at a number written out, anything that isn't a zero is a sig fig. Okay, that one's pretty straightforward. It's the zeros that are confusing. There's 3 kinds of zeros. Did you know that? There's 3 kinds of zeros. The first kind are called interior zeros or trapped zeros. So you see this zero? It's stuck between a 4 and a 3. It's not at the beginning. It's not at the end. It's stuck in the middle. Those always count. Here's one that's stuck between the 3 and a 2, and here's one that's stuck later in the number. Those are also interior zeros, so they count. Leading zeros, these are the ones that come at the front of a number, and usually you only see them with numbers that are less than 1. So 0.00023. The purpose of those zeros is to locate the decimal point. They don't really reflect measurement, right? Now, what if you had the number 4044.5? Could I put some zeros in front of that?
No.
Well, I could. It looks dumb, but it doesn't change anything. They're unnecessary. That's why we don't write them. How many of them would you write? Well, you could write any number you want. Those are not significant figures. We don't write them here because we don't need them to hold the decimal place. But for these numbers, we need them to hold the decimal place. Because if we say, well, it's 0.23. I left space. Yeah, how many spaces is that supposed to be? We don't know, so that's no good. So the numbers at the beginning don't count. Then there's trailing zeros. So these rules here are worded a little differently than what's in the textbook. They give the same result. This is what makes more sense to me. So those trailing zeros, the ones at the end, those are the guys that cause all the problems. So they're significant if there's a decimal point written in the number. Doesn't matter where the decimal point is, if there's a physically written out decimal point. So here, 39.0, that's a trailing zero. There's a decimal point. It's going to be a sig fig. Trailing zeros before implied decimal points are not significant. Technically, they're ambiguous. We don't know if they're significant or not. We want to avoid them, but sometimes we encounter them. And what we want to do is we want to assume the worst, and so we'll call them not significant. So we look at this number 300. Those zeros there are needed to hold the decimal point, right? Because otherwise it would be 3. 300. We need those zeros. But do those necessarily say that we measured those with certainty? No. We can't tell. It's ambiguous. But here, 39.0. Did I have to write the 0 to hold the decimal place? No, there's an actual decimal point. I don't need it. Why did I write it? Because I measured it. Okay? So here, 120.00. It doesn't matter if the 0 is before the decimal point or after the decimal point. It just matters those are trailing zeros and there is a decimal point. You count them. Okay? This is going to take a little practice making mistakes and we'll figure it out. So then there are also things called exact numbers that have no uncertainty. These are not measurements. So an exact number might get used in a calculation, but since it has no uncertainty, it's not going to affect the uncertainty of the final answer. So what do? Well, you can just leave them out of the process in terms of looking at significant figures, or you could think of them as having an infinite number of significant figures. So these are going to be things like exact counting of discrete objects. So I don't have 2 pencils, but I have 2 Surface Pro tablets. Is there any uncertainty in how many there are? Are you sure it isn't 2.5? Yeah, I'm sure. It's 2, right? You can count that. 1, 2. So counting objects, integral numbers, integers, whole numbers that are part of an equation. The diameter of a circle is equal to 2, exactly 2, times the radius. So that 2, we didn't say that has one significant figure. That's an exact number. We don't have to think about it. Or defined quantities. A gallon is defined as being exactly 4 quarts. Now, with those conversion factors, we have to be, it gets a little muddy, because if you stay within the English system, if you're talking about gallons and quarts and tablespoons and teaspoons, all those relationships are exact because they're within the same definition. If we're in the metric system and we're looking at milliliters and microliters and kiloliters, the relationships are exact. If we're going from quarts to liters, that's not an exact conversion. The number of significant figures you have there will depend on where you look the number up, right? It's not going to be exact. So let's practice this. So 554 kilometers, how many significant figures is it? It's 3. That one was nice because there weren't any zeros. 7 pennies. That's an exact number. Those can be tricky because you look at the 7 and you say 1 sig fig. Oh, but it's 7 pennies. We can count those. So we could say that's an infinite number of significant figures. This one's in scientific notation. 1.01 times 10 to the 5th meters.
6.
We haven't talked about this. We will briefly go over scientific notation, but in decimal notation, you would write it like that. So these end up being trailing zeros. There's no decimal point, and they're ambiguous, right? This zero is good. It's trapped, right, between two non-zero digits. But we don't know. And this is the downfall of using decimal notation with large numbers, is you end up needing all these trailing zeros. When we put this number into scientific notation, the decimal point is always after the first non-zero digit. So if there's a zero in your number, there will be a decimal point. And this times 10 to the 5 business takes care of where is the decimal point. So in scientific notation, you just look at all the digits before the X. They're all significant. And we can apply the rules to that as well, because we have a trapped zero here. If it was 0.00, there's still a decimal point. So that one's going to have 3. Any questions about that one? Does that make sense? How about 0.00099 seconds?
6 because there's a decimal. 2.
2. So 6 because there's a decimal point, you said. Very reasonable thing to say. So it's, again, there's 3 kind of zeros, and the decimal point thing only applies to one of them.
So if there's a 1.00099, it would be 6.
Mm-hmm.
That's
Yeah.
almost it again.
Yeah, it's tricky, and this one gets a lot of students. And, yeah, we just need to...
Semester in this class I mess up on this.
That's okay. We can get better at it, right? You don't get it yet. So these are the leading zeros. Zeros at the beginning never count, because they are always there to hold a decimal place. Zeros in the middle always count. Right? It's the zeros at the end where we say, if there's a decimal point, they count. If there's not a decimal point, they don't count. So 2 is correct for this one. What about letter E, 1.4500 kilometers?
3. 5.
5. What kind of zeros are they? Trailing. Right? I told you, zeros are confusing. Leading, never. Trapped or interior, always. Trailing. The ones at the end, those are the ones you have to worry about. So, yes, if there's a decimal point. No decimal point. The best answer is they are ambiguous. If you're forced to choose, then you'll say they're not significant. So this one, those trailing zeros, we use this rule here. So there's a decimal point, so they count. How about 21,000 meters?
2 because they're trailing with the decimal.
Yeah. So technically, we would say this is 2 significant figures, the 2 and the 1, because here we have trailing zeros. There's a comma, but a comma isn't a decimal point. So this 2 significant figures, it's ambiguous. What if you measured it to the nearest tens place? Well, one thing we do kind of in notes to ourselves is we will underline the last significant figure. That's the uncertain digit. And if you're lucky and you're writing this number and somebody else is reading it, maybe they understand that convention as well. But maybe they don't, right? And it still gets a little awkward underlining things. Yes?
So does that mean you can say for the 101,000, if you put a comma, technically it's also 3, but ambiguous. You write it
Right.
the same way as that one.
Yeah, so if I write this out like this, 101,000, then I would say that one's 3 or ambiguous. Yep.
We would just write A and B.
I would just do 3. So, oh, that's not what I wanted to do. So what if I did mean that this is to the nearest 10? The best thing to do is to put it into scientific notation, because the trailing zeros all go away. So scientific notation, what we're doing is we're going to look at where the decimal point is. It's not physically written there, but we know where it is, right? It's right here. And we're going to move it over here. And we're going to see how many places do we need to move it? 1, 2, 3, 4 places. So 2.1, and then I want to keep all of the significant zeros. So I underlined this, right? So these first 2 are significant and the last one isn't, just because I decided in the example. And then we have times 10 to the, and 4 is the number of places, so 4 is the exponent. I wrote both of these zeros because in my little shorthand notation here, I had indicated that this 0 was the uncertain digit. And I'm going to keep the uncertain digit. So that one is right here, and I need to keep anything before that as well. Another common thing that happens is students get confused about should that be a negative 4 or a positive 4. So this is how I think about it. Is 21,000 a big number or a small number?
Big number.
It's a big number. What are my feelings about big paychecks? Positive or negative? Positive. I have positive feelings about big paychecks. Positive exponents for big numbers. If you have a negative exponent, it means it's a small number. The book tells you you're moving the decimal place to the right or to the left. I can't keep those straight. I just think about paychecks.
Are you positive about your paycheck?
Usually, yeah. You guys doing okay or do you need a break?
Inconclusive.
Inconclusive. Okay.
Ambiguous.
We'll just, yeah, ambiguous. We'll just keep going then. So, when we do calculations, we shouldn't be gaining or losing precision. So, if we're multiplying and dividing, and this is probably the most important type of calculation that we need to understand significant figures for. This is the rule. The result, the answer, is going to have the same number of significant figures as the factor, the thing that we are multiplying or dividing, that has the fewest number of sig figs. So looking at these examples, 1.052, that has 4 significant figures. That's a trapped 0. This one, 12.504, has 5 significant figures. Again, a trapped 0. This one, 0.53, the zeros at the front don't count, so this one just has 2 significant figures. And then you ask yourself, well, which is smaller, 4, 5, or 2? Well, 2 is the smallest number. This is the smallest number of significant figures. So you do the math on your calculator and you write down the whole answer. And then you say, oh, but this only had 2 significant figures, so I need to round this to 2 significant figures. And then you round it. I would encourage you to always write down your answer with some extra digits. You don't necessarily need to write all 9 decimal places that your calculator spits out at you. But what I would do is I would look at this and say, oh, I need 2 sig figs. I should write at least 2 extra ones. Just write a couple extra ones and then round it. So here we have division. This number is 5 sig figs. This one's 3 sig figs. Again, there's that trailing 0 with a decimal point. It counts. So 3 significant figures is the smallest number of significant figures. And so over here, I'm going to round to 626. I'm going to round to this place. And when we round up or down, we're just looking at the next digit. If it's 5 or greater, you round up. If it's less than 5, you round down. Adding and subtracting, gives students more trouble. The good thing is, in lab, when we're adding and subtracting, you're not going to get a crazy number of digits, right? It's only multiplying and dividing where the thing explodes. But the rule here is the result's going to carry the same number of decimal places as the quantity with the fewest decimal places. So those rules are very similar. So if you're multiplying or dividing, you're counting sig figs. If you're adding or subtracting, you're counting decimal places. It's still the fewest. So here, adding these numbers together, this one has 3 decimal places. 2 decimal places is different than the number of sig figs. And this one has 4 decimal places. Smallest number of decimal places is 2, so the answer gets rounded to 2 decimal places. It can be helpful when you're trying to get this clear in your head to write them out stacked up like you weren't going to use your calculator and see which number ends first and then draw a line, because that's where your answer is going to end. So here's an example, 5.9 minus 0.221. This has 1 decimal place. This has 3 decimal places. The smallest is 1, so we can only have 1 decimal place in the answer. Where students make a mistake with adding and subtracting, most commonly is where you get something like 5.5 minus 0.5. So what does your calculator tell you? It tells you 5.
But
The answer is 5.0. Because both of these numbers had 1 decimal place. So my answer needs to have 1 decimal place. Because this was an estimated digit and an estimated digit, and I need to keep an estimated digit. There's no uncertainty in that digit. 5 minus 0 is just 5. We need to keep an estimated digit. When rounding, round down if that digit that you're dropping is 4 or less. Round up if it's 5 or more. So this is really important. You have to be really careful when you're rounding numbers in the tens place, hundreds, thousands, because sometimes people stop thinking and they just chop off the number and they change the value of the number. Excuse me. So let's do an example here. So let's say this is the price of a car, maybe. $24,938.99. We're going to round this to 3 significant figures. So 1, 2, 3. I'm going to keep 3 significant figures. And then I'm going to look at the next digit to decide whether I round it up or down. Well, that's less than 5. So is that $249? No. I'm rounding to the nearest hundreds place, right? So I need to keep the value, keep the value, overall magnitude of the number. So this is still 24,000 something, right? I can't round 24,000 to 2,400 or 240 or 24 or anything like that. So be careful. So to avoid that, if where you're rounding is further over than the ones place, put it in scientific notation, and then it won't happen to you. So if I was going to do scientific notation, I'd be 2, and you always put the decimal after the first digit, never the second one, it's just always the first one. People do some really strange things. 2 point, and I'm gonna keep the 4 and the 9, that's my 3 sig figs. And I check that I don't need to round the 9 up. And now that's gonna be times 10 to the something. Well, I kind of made a mess over here. So I'm moving the decimal point over there. 1, 2, 3, 4 places. So my exponent is 4. Positive or negative?
Positive.
Positive. Because 24,000 is a big number, and I feel positive about big paychecks. So this would be 2.49 times 10 to the 4th dollars. Yeah.
Real quick, kind of leading back to what did you say, the concept of sig figs with addition and subtraction.
Mm-hmm.
Would you say that, say if it was 1,000.1 and then 0.07, would 1,000.1 be that lower decimal place?
Mm-hmm.
Okay.
I don't know what's going on here. So 1,000.1, and what was the other one?
Like 0.07.
0.07. And whether we're adding or subtracting, the rule is the same. So this one has 1 decimal place. This one has 2 decimal places. So the answer will only have 1 decimal place. And I can show you a couple of other ways to help you understand that, but I'm not going to do it in lecture right now. If you ask me later. Any other questions? Quick thing about rounding, and this is, could be a test question. I'll give you a number, round it to 2 significant figures. So I'm keeping the 5 and the 3. I look at the next one. It's 5 or greater, I round up. So this is 5.4. If it was 5.34, that digit I'm dropping is smaller than 5, so I just call it 5.3. Because we're looking, is this number closer to 5.3 or closer to 5.4? That's what rounding is doing. 5.35. Well, the rule says we round 5 up. And so this is 5.4. Here, this one has more digits on it. I don't need to look at that 9 at all. I'm only going to look at the first one that's going away. Occasionally people get carried away and they want to start at the end of the number, round up and down all the way until they get to the uncertain digit. That's a lot of work and sometimes gets you the wrong answer. So I'm going to keep the 3. I'm only looking at the 4. Don't look at the 9.
There's like this saying, 5 or more raise the floor, 4 or less. I can't remember.
Never heard that one.
I can't remember where. I think it was like in elementary school.
Probably.
Only half of it is carried over.
Maybe you could look it up later. Okay, rounding in multi-step calculations. So sometimes we add a couple numbers and then we take the result of that and we multiply it by something else and then we might subtract something. We do a lot of different operations, right? We get these intermediate answers. We don't want to round those. Because when we round those, a lot of times it's not going to make any difference in the final answer, but sometimes it does. So what we want to do is we want to keep some extra digits. You do not have to keep all of the digits. What I have figured out is if you keep 2 extra digits, so I need 3 sig figs, I'm going to write down 5. If you keep 2 extra ones, you don't even have to worry about whether to round that last one or not. You could just write it down as your calculator says. Keep 2 extra digits. But you want to keep track of what's going on by underlining the last significant figure. So I kind of started doing that already, showing you with those zeros. Well, we could underline one and say that's the uncertain digit. So in this example, we're multiplying these numbers, and here there's a subtraction, and then that quantity is multiplied, right? So we have to apply the rule to each operation. We can't just look at the overall. And I'm sorry, but it's just how it is. So on the worksheet, there will be questions that will try to trick you on this, okay? on the exam, the question might try to trick you on this. The rest of the semester, I'm not trying to trick you on this. I just want you to do your calculations correctly. So when we're subtracting here, the fewest decimal places is the 5.01. So the answer to that would be 0.479. That's what your calculator would tell you. I'm going to underline, the second. Well, yeah, they already did. Never mind. So I'm underlining the second sig fig, the second decimal place, because that's what the rule for subtracting tells me. If I was just doing this part and this was the answer, it'd be 0.479, and then I would round it and call it 0.480. 0.48. But I'm not done yet. So I underline the last significant figure. Now I'm going to do the multiplication. So now I'm looking at number of sig figs. Okay? 3 sig figs, 4 sig figs. There's 3 digits written there, but only 2 sig figs, because I'm only going to count up to the underlined one, because that's the last one. So this is 2 sig figs, and so here's what my calculator shows me, and then I'm going to round to 2 significant figures. Okay? It's going to take a little bit of practice. Yeah.
You lost me on the last part with the 2 significant figures.
Okay. So, thank you for asking, because I'm sure a lot of people got lost. So, you're okay that when I did this, I should have 2 sig figs, or 2 decimal places, right? From the subtracting?
Oh, that's right, it's decimal places, that's why it's 2 sig figs.
Yeah. Yeah. So we get 0.479, but the 9 is after. So if I was stopping there, I'd say it's 0.48, 2 decimal places, right? Well, rounding this from 0.479 to 0.48 might cause a difference in my final answer, so I don't want to do that yet. But when I'm doing the multiplication now, I'm looking at this number, 3 sig figs, this number, 4 sig figs, and this guy, the 9 is in there, but it's not a sig fig, that's 2. So when you've got multiplication, subtraction mixed together, you cannot look at the fewest number of sig figs or the fewest number of decimal places in any of your starting numbers and just get the answer, right? Because it's complicated. You know, if I could recreate math, I'd do it differently, but you know, it is what it is. It's nothing that anybody did to anybody. Does that help? Let's just do one of these. A, B, C, or D. Actually, let's do C or D. C. Let's do C. Okay, up here, we've got multiplying and dividing. You just have to count sig figs. Here, you've got adding and subtracting. You're looking for fewest number of decimal places. But C and D are mixed. So this is multiplying, this is dividing, and here's adding. So the adding is in parentheses here. So what I want to do is I want to do that adding, 44.11.
45.323.
Thank you. So the answer there is 45.333. And then I need to identify the last significant figure. Adding is decimal places.
45.3.
Yeah, so 2 decimal places, because this one has 2 decimal places. This one had 3 decimal places. I'm adding, I'm looking at fewest decimal places. Now I'm going to multiply and divide. So I'm going to do that and write down the answer. So 2.5110 times 21.2 divided by 45.333.
Should I include that zero?
Yeah, these zeros are significant zeros. Sometimes I forget to say them when I'm talking to myself, because if I leave this 0 out of my calculator, does it change anything? No, it doesn't, because my calculator doesn't understand sig figs. So you can leave those out if you're like, but that's confusing. Put it in. It's not going to hurt anything. Do what's least confusing, right? So I'm getting this crazy answer here, 1.17. I'm like, I don't want to write out all those numbers. Well, I can identify now how many sig figs my answer should have. How many sig figs in this number? 5. Trailing 0, decimal point. How about this number? 4. And how about this one? 4. We wrote the 3, but we underlined this 3 to remind ourselves that's the end. Okay, so smallest number is 4. My answer should have 4 significant figures. So what I'm going to do is I'm going to write down 4, 1.174. That's the 4th one. And I'm going to write down 2 more digits. 27. That last one, you can round it correctly if you want, or you can just write what it is. It won't make any difference. And then for my answer, I'm going to round this to the correct number of significant figures, and there's my answer. So the advantage of writing this down is that sometimes, especially in lab, you find that you need to take one of those previous results and do more calculations with it. But you're not supposed to round it for the calculations. So if you've written down 2 extra digits there, you can use that in your calculation and you'll be fine. Okay? If you really want to write down all of them, you can. This is kind of tedious, right? Any questions?